Hello students, today we will be dealing with a very important principle in the fluid mechanics, that is called the Bernoulli's principle. Now the Bernoulli's principle is basically the conservation of energy, so we will be trying to understand how do we apply the conservation of energy in fluid mechanics. So let's start the topic. Bernoulli's equation. Now let's see what exactly is this Bernoulli's equation. Now the Bernoulli's equation is actually the statement of conservation of energy. The Bernoulli's equation is not any special law, but it's simply the conservation of energy. When you apply the conservation of energy within a fluid, within an ideal fluid. Now all of these laws, they are valid only for the ideal fluid. When we apply the conservation of energy within an ideal fluid, the equation that you get is called the Bernoulli's equation. Now if you see, if I try to apply the conservation of energy to get the Bernoulli's equation, what are the forces that are doing the work? Now if you see at this point, there is a pressure, there will be pressure that will be acting. Now this pressure comes from, it could be converted into the term of force. So this pressure is actually doing some work. So now in this fluids, we normally call this work done by the pressure is pressure energy. This pressure will cause the displacement, that displacement will do the work, and that gives you in the form of pressure energy. Now if you consider this element of the liquid that we have considered, now this delta L1 is, suppose it's moving with V1, it's V1 times T, if you consider in time T, and in the same time T, if you see, this is, if you consider different section exactly at the end, here this is moving with V2 velocity. Now here the work done by pressure will be again called pressure energy, that was here. Now here it's moving with V1T. Now this element that you see, this cylindrical section, it has come to this height. So if you consider like a center of mass part, that is center of mass was at height Y1, now this is at height Y2. So when we are applying the conservation of energy, we can see that the potential energy has increased of this element. Its potential energy has increased. Apart from that, you can see that the kinetic energy, here it was V1, since the area of cross section had changed, what we have seen in the equation of continuity, the velocity has changed. Velocity change means its kinetic energy has same, because its kinetic energy has changed, because this mass that you see is the same as this mass, because the volume flow rate is a constant. So the mass that is flowing out, or the volume that is flowing out, is same in any time t. So the mass of this one is same as the mass of this one, but the velocity of this mass is different than the velocity of this mass. So its kinetic energy is different. Its potential energy is different based on Y2. Its potential energy based on Y1. Then there is a pressure energy. Now the other force that is present here is the normal force by the contact surfaces. Now as you can see here that this normal contact force is perpendicular to the velocity of the light. The velocity of fluid that is given here. The velocity of the fluid is in this direction. Normal reactions are acting like this from the top end, and then from all the directions like this. So these normal forces, they are not doing any work on this flow of the fluid, this velocity of the fluid. They are doing no work on this. That means if you apply the conservation of energy here and here, if you balance this, what we get is this equation, that the pressure at this point, that is P1 plus half of rho V1 square, V1 is the velocity at this point, plus rho g Y1, Y1 is this height of this element, now is equal to P2 plus half rho V2 square plus rho g Y2, all of the corresponding terms at this places. Now this term that you see, this is the pressure energy term. This is the pressure energy term. This is the kinetic energy term. This is kinetic energy term. And this term that you see, this is the potential energy term. Okay, now this thing is a constant throughout the liquid, even if you consider this section here at this point. If we apply the Bernoulli's equation at this height, you will have this value. This is equal to, if you have pressure here is P3 plus half rho V3 square plus rho g Y3, whatever is the height of this. So this is the Bernoulli's equation. Let's see some questions based on Bernoulli's equations. Now in this question, it's given that the gas flows from left to right. It's going like this through this pipe whose interior is hidden. You don't know about this, its interior. It's not known to you whether the area of cross section here is greater, what kind of cross section is actually it is. At which point does the pipe have the smallest inner diameter? And the question says where it has smallest inner diameter. Now if you see here, the liquid is at this height here, liquid is at this height here, and the liquid is at this height here. Now since these are all the same liquids, okay, since these are all the same liquids, that means the pressure that is acting at this point is same. What does it mean? That means that the pressure at this point is highest in the air. If you consider this portion, it's highest. Pressure at this point plus rho GH will be equal to the pressure at this point. Pressure at this point plus rho G, this height, will be equal to the pressure at this point, and this is what the pressure at this point exactly is, which is greater than this. So highest pressure here means, if you apply the Bernoulli's equations, now A, B and C, they are all at the same height. If you see from here, they are all at the same height from this place, bottom. So we will only apply P1 plus half rho V1 square, P2 plus half rho V2 square is equal to P3 plus half rho V3 square. Now if you see here, the pressure here is greatest, so P3 is greatest, then comes P1, then comes P2. Now if this is greatest among all these two, and the sum of this two are equal to sum of this two are equal to sum of this two, that means if this is greatest, then V3 has to be lowest, because the sum is a constant. So V3 is lowest, that means V3 is less than V1 is less than V2. Exactly in the reverse order, because this whole thing is a constant throughout the section. Now if you see, you have got the relation between velocities. Now applying the equation of continuity, we know that AB is a constant. That means that will give you A1 V1 is equal to A2 V2 is equal to A3 V3. Now if you see, V2 is greatest. So if V2 is greatest, A2 will be smallest. V3 is smallest. V3 is smallest means A3 must be largest, because again the product is a constant. So if something is becoming smaller like velocity, the area must be larger value compared to these any other constant values that you have. That means the point B, what you had here is V2 you had the largest velocity. V2 has the largest velocity means A2 is smallest, so it's point B. Point B has the smallest inner diameter because it has the smallest area of cross section. So you can see how we are applying the Bernoulli's equation and equation of continuity. Now this question says that the pressure of water in a water pipe when the tap is open and closed are respectively this. With open tap, the velocity of water flowing is, let's make a tap. This is a tap. Now it is given here that the pressure of water in the water pipe when the tap is open and closed. So suppose it is closed. So when it is closed, the pressure will be, let's take that pressure as P1, PC. Pressure is closed. Okay. Now since this is closed, the velocity of the water at this time is 0, because the liquid is not flowing, it's closed. And we take this height as height for our potential energy consideration. So that Y will be 0. That means if you write the Bernoulli's equation for this, it will be pressure will be P plus rho Gy plus half rho V square. This is 0 because it's not flowing, the tap is closed, and this because we can choose our reference level of the potential energy. As we know, it's discretionary, so we have chosen this as the height, so we get only PC. Now when it is open, when you open it, what will happen? The pressure will become, let's denote this by PO, pressure open, and then it will have some velocity. It is moving with velocity v, suppose v. Again the liquid, if you are considering the liquid at the same height, the y is again 0. That means again if you apply the Bernoulli equation, you have P naught plus half rho v square, because now v is finite and this is again 0. Now these two have to be equal from the Bernoulli's equation. So that means if you equate these two, you have Pc is P naught plus half rho v square. That means we have Pc minus P naught into 2 by rho is v square. That will give you the velocity is twice by rho Pc minus P naught. Now putting the values that have been given to us, what we see here is that 2 by rho. Now since this is water, the density of water is 1000 in terms of SI units. Pc minus P naught, this pressure closed one is this and open one is this. So Pc minus P naught is 0.5 into 10 to power 5, that gives you 5 into 10 to power 4. So if you see, this is 5 into 2, 10. So this becomes 10 to power 5 by 1000. So this means you have root over 100. That means what you get is 10 meter per second. So if you look at the options, okay, so B is the correct option.
So students, we have seen what exactly is the Bernoulli's equation, how the conservation of energy principle manifested itself in the fluid mechanics. Now after this we will be going to deal with some of the topics that are actually associated with non-ideal fluids, in which we will be discussing viscosity and surface tension. So stay tuned with Ask IITians for the next topic.